have me climbing Mount Everest or something like stuff like that. Skydiving, whatever you want.
I also give a brief personal bio for you.
That's as you should. Okay. So like the second derivative now.
It's the curse of understanding these things. You actually start thinking about it. New crew just showed up. Oh, well.
So you just went up again.
Russ just came in. That must be supposed to be the group he rounded up.
I see. So Mark, I think you can sit on this side because that's where all the microphones are.
Right. Yeah. And then I'll go sit down. Welcome. On behalf of the Department of Statistics and the Robotics Institute at Carnegie Mellon University, I want to welcome all of you to the 12th Morris H. DeGroot Memorial Lecture. It was 22 years ago that Maury died. Those of the younger generation of statisticians and robotics people and machine learning people, of whom I see many here, you probably never got a chance to meet Maury. Even those of the older generation, amongst which I must count myself, if you didn't attend the late night parties and at the various Bayesian meetings, you probably never got a chance to meet another important version of Maury either. But I think that all of us have been affected by the legacy that he left us through his contributions in research and education. His Optimal Statistical Decisions book is, of course, a classic. His Probability and Statistics text has taken on new life in part due to the example that he set. I learned a lot about how to teach statistics from studying his writing style. Maury's research in decision theory, statistics in the law, psychiatric statistics, economics, and other areas is profound. He was one of the founders of the series of Valencia meetings, which had a huge impact on the advancement, visibility, and quality of life amongst Bayesian statisticians worldwide. He was also the founder of the Department of Statistics here at Carnegie Mellon, which has had a huge impact on the quality of life of a lot of people here today. In addition to being a world-renowned statistician, he was a good friend to his colleagues and an outstanding mentor to new statisticians. Many were the times that he helped me in my career. I remember one day in his office he handed me 2 recently published books on multivariate analysis, including the second edition of T.W. Anderson's classic text. He said that he would like a review for statistical science, but not so much a book review as a review of the field. And this gave me a great opportunity to think about both the history and the future of the field, and I didn't hold anything back. Maury did not give me any grief about what I wrote. On the other hand, I did earn a lifetime ban from Stanford University. I learned a lot about being a professional from studying Maury's interactions with colleagues. I feel truly blessed to have had the opportunity to know Maury DeGroot both professionally and personally. He lived only to age 58, but he accomplished so much. Shortly before Maury died, he took a belated interest in computing. In the old days, Maury was the only department member who had a dust cover for his cathode ray tube terminal in his office. But at the end, he wanted to start working on a PC. If he had lived, I think he would have been pleased with the degree to which statistics and computation have helped to advance each other. And I'm sure that he would be pleased with today's speaker. Daphne Koller is a leader in the transformation of artificial intelligence from a theoretical to a practical discipline. In addition to artificial intelligence, she has a good helping of natural intelligence. For example, when explaining what she does to the popular media, she tells them that the world is noisy and messy. Most people don't figure that out until after they visited my office. Her contributions extend to game theory, molecular biology, genetics, and more. According to the New York Times, Daphne's work builds on an 18th century theorem about probability. Yes, okay. Newsweek magazine named Daphne one of the 10 most important people of 2010. We think she's even more important this year. Indeed, she's on her way to Washington, D.C. to be inducted into the National Academy of Engineering this weekend. And so I look forward to a great lecture by a prolific member of our field in honor of a wonderful friend and colleague. I give you Daphne Koller.
Thank you, Mark, for the introduction, and I'd like to thank the Statistics Department and the Robotics Institute for inviting me to be here to honor a man whose work has had a profound influence on my own thinking and on the thinking of many of us in this room. And I'd like to thank all of you who came to be here despite the AI stats deadline in 3 hours, so thank you for that. So what I'll tell you about today is on a body of work that I've been working on in my group, or that my group has been working on learning richly structured representation from weakly annotated data. And much of the motivation from that work comes from the work that we're doing in computer vision. So I'll talk a little bit about that at the first part of the talk, and then delve more into the statistics and the machine learning component in the second half of the talk. So the goal of many of us who are working in computer vision is to try and go from perception to understanding. So to try and take an image such as this and to turn it into a verbal description of the type that a person might use to talk about this image. So a man wearing a backpack, smoking a cigarette, walking a dog. Now the problem with this is that while this is very easy for humans to interpret the image in this way, when you think about how computer vision works, we discovered that it's really quite hard, because most of computer vision, at least up until the last 5 years or so, has really tried to look at little pieces of the image and interpret them in isolation of everything else. And when you do that, you realize that, for example, the cigarette is about 3 pixels wide and maybe 8 pixels long, and it's just an undifferentiated white stick that occurs in many, many other places in the image. And the only reason we know that it's a cigarette is because of the placement in the man's mouth and some amount of...
The microphone isn't on.
Okay. I was reading...
Yeah, it says off.
That'll do it. Okay, well, I'm not going to start over. So it's something that the only way that we know what it is because of the placement in the man's mouth and some amount of training that we have over time about the fact that things that stick out of people's mouths that are small and white are either cigarettes or lollipops, and probably this is not a lollipop. Similarly, the backpack is an undifferentiated black blob with very few distinguishing features, and only contextual information gives us an indication of what it's likely to be. And so the notion of the problem of interpreting a scene in its full glory with high accuracy, I think, really rests on the notion of holistic scene understanding, which is what we're trying to work on. So let me contrast the goal of holistic scene understanding with a slight caricature, but not too much of a caricature, of how computer vision works today. So a key task in computer vision is object detection, where we're trying to find, for example, all instances of a car in an image. So how does that work? We give the algorithm a bunch of what are called bounding boxes. These are boxes that contain cars. Those are the positive examples. We give it a bunch of bounding boxes that do not contain cars. Those are the negative examples. We apply our favorite machine learning algorithm, whatever should it be, and it learns to distinguish the yes cars from the no cars. And then when given a new image as input, what happens is that we put a bounding box on, say, this corner of the image, and we say yes car, no car. Then this one, and this one, and this one, and this one, and this one, until we're done with the image. Now, of course, we don't know the aspect ratio of the car because it could be close in or it could be far away, and so we have to do this at different granularities as well. And so ultimately, after we finish running all of the bounding boxes on the image, what comes out of the algorithm is something that looks like that. So here I've put in, this is a reasonably state-of-the-art algorithm, probably not the best today, but pretty reasonable, cars, people, and motorcycles. So you'll notice that it actually caught this person here, but that too is a person. What's more interesting is that that is a motorcycle. And if you squint at it, you can kind of see that these bowls of leaves look kind of like wheels of the motorcycle. You can kind of see why a machine learning algorithm might interpret this to be a motorcycle, even though we as humans realize that this cannot possibly be a motorcycle given where it's placed in the image. Which is why contextual scene understanding is so important in trying to improve in trying to at least reduce the ridiculous mistakes that are made by the algorithms that we have today. So what I'm going to talk about, as I said, the talk has two parts. I'm going to start by talking about holistic scene models, and I'm going to give you two vignettes of work that we've done, one focused on indoor scenes, one focused on outdoor scenes, and then I'm going to talk about latent variable models and how to learn better with latent variables. Okay. So this first project was led by my graduate student Wang together with my former graduate student Stephen Gould. So the goal here, and this was actually a project that received a lot of attention here by colleagues here at Carnegie Mellon, to take an image of an indoor scene and to recover from it both the global geometry, that is where are the walls, where do they meet each other, where do they meet the ceiling, as well as the layout of the furniture in the room. And the problem is that this is actually much harder than you think it is, and if you start looking at some more cluttered rooms, maybe like Mark's office, you find that rooms tend to be cluttered, and that there is and that this clutter occludes the boundaries between the walls and obscures the appearance of faces, so that it's not that obvious as it might be in this image where one wall ends and the other begins. So in a paper, in a pioneering paper by Hidao et al. In ICCB 2009, they took a supervised approach to solving this problem. They took an image and they hand-labeled it, giving both the labeling of the box as well as where the furniture is. So pixel by pixel annotation of what is furniture and what is not. And then they train an algorithm that iteratively kind of iterates between these two pieces, between two learners, two learned models, one that estimates the box, and the other one that tries to classify what's furniture and what's not, and each of those uses the output from the other to hopefully improve its own performance. So if you know where furniture is, you might be less confused by that when trying to estimate the box and vice versa. So this is sort of the approach that they took. We decided to take a very different approach, and you'll see that latent variables are a running theme in this talk. So we decided to basically not try and get a human to label where the furniture is. The only labeling that we got for training was where the boundaries of the box were. And the idea is that we were going to model, so we weren't going to ignore the issue of clutter or furniture, but we were going to model it as latent variables. That is, things that were not given to the algorithm, not only not in testing, but also not in training. And that's what I'm going to use latent variables to mean throughout this talk. And then we're going to use max margin learning, which I'll talk about in the second half of the talk when we get to the sort of machine learning part, of the joint model of the clutter and of the box that specifies the room. So how do we do that? We first define an energy function. An energy function is our optimization objective that tells us which interpretation of the image we like the best, and we're going to try and optimize this objective. So here, X is going to denote the image, Y is going to denote the box parameters, and H is going to denote the latent variables, which is this binary mask that tells us for each pixel whether it's furniture or non-furniture. Now, this gives us, so these are sort of the variables on which the model is run. And then for each such possible assignment to the variables, so notice that X is given in the input always, Y is only given in training, and H is never given at all. But for any given assignment of X, Y, and H, we can define a set of features that tell us whether this makes sense as a joint assignment to these variables. And these features tell us, measure things like the consistency of the color of the walls and the angle between one wall and the other, and all sorts of other whatever features you might want to include that might indicate to the algorithm how good of an interpretation this is. And then for each such feature, the algorithm learns a weight that says how important it is and does it have a positive or a negative influence on the quality of this model. And so the goal of the learning problem is to train this weight vector W. But given a weight vector W, we can now interpret the image by finding the y and the h that maximize or minimize, depending on how you want to formulate this energy function. So we did that initially and discovered that latent variables, as any of you who've worked with them know, are actually fairly tricky beasts. So this is the inferred box in our initial attempt to do this. And I'm not going to I'll talk about the learning part a little bit later. And this is the inferred clutter. And basically you realize that the algorithm took pretty much in this image, took pretty much every single thing, every single pixel, and inferred it to be furniture. And here it took everything but the furniture and inferred it to be furniture. And that's because latent variables are intrinsically hard to identify. They're ill-defined, and so the algorithm has too many degrees of freedom to find an interpretation of latent variables that just doesn't make sense and therefore leads to bad performance. So how did we solve this in this case? We basically tried to ground the latent variables using some prior knowledge about what a sensible interpretation is. Now, we didn't want to over-constrain it, but we wanted to constrain it a little bit. So instead of just having this data-driven term, we had an additional prior term, if you will, which actually has two different pieces to it, which you can call E1 and E2. And E1 roughly says that major faces, such as walls, should have consistent appearance in terms of color and texture if we take out the clutter that's occluding those walls, which is kind of a sensible thing because walls don't tend to be psychedelic. They tend to be fairly uniform in appearance. And so if we take out the stuff that's in front of them, they should be pretty uniform. The second term basically just stipulates that there shouldn't be too much clutter. That is, despite Mark's office, there should be enough parts of the wall and ceiling visible to avoid this error mode that we saw previously. And so we added into the energy function these two terms, and then that gave us an informed prior about the latent variables, which we introduced into the learning process, and that gave us better imputations of the latent variables and therefore better models. And so if we look at what we got now, if we now see what we get when we learn with the prior terms compared to learning without the prior terms, this is the same slide that I showed before, you can see that now we get a much better imputation of the clutter simply by grounding it in a very minimal amount of prior knowledge. So let me show you some quantitative results. These are qualitative results. So this is from the Hadao et al. Paper that preceded ours by 1 year. So they actually had two different regimes, one that was unsupervised and where the clutter or the furniture wasn't labeled in the training set, and one that was supervised. And so 25% error approximately in the unsupervised regime and about 20% error in the supervised regime. Our method, which uses an unsupervised data set, got better performance despite being unsupervised than in the supervised regime. Now, what's even more interesting is that if you go and you give the algorithm the ground truth clutter, that is, even in the test set, you give it what the human labeled as the clutter, the performance degrades. Okay? So the human labeled annotations are worse for the algorithm than the inferred latent variables. So you might wonder why that is. And if you look at this, these are three example images. This is our inferred clutter, and this is the human hand-labeled clutter. And you'll see that many things that our algorithm chooses to declare as clutter because it's instrumental, it's helpful to the performance of the algorithm, are actually not labeled as clutter by the human. The lamp on the bedside, this entire piece of furniture wasn't labeled as clutter by a human. And I have even better examples. Here, nothing was labeled as clutter by the human, which basically suggests that human labeling for latent variables, what humans consider the right labeling for a latent variable, might not be what the computer requires for optimal performance. And that's going to be, again, a theme that runs through this talk. Okay, so that was the first vignette. The second vignette has to do with work that we've done on understanding outdoor scenes, and that you'll see that latent variables are a theme here also. This was the PhD thesis topic of my post of my PhD student Stephen Gould that was then greatly expanded by my postdoc Pawan Kumar and Kianchi Da. So outdoor scenes. So here we would like to take an outdoor scene such as this, and we would like to label each pixel in the image. Again, we were doing a pixel level labeling. We'd like to label these pixels as roads, this is a car, this is a bus, and so on and so forth. We'd also like to figure out the scene geometry, so which of these are horizontal, which are vertical, and where the horizon is and where's the sky. And so here again we have an input x and an output y, and at this point we don't have latent variables. I'll introduce them in a little bit. And so again we're going to define an energy function, and we're going to try and find the annotation y that optimizes this energy function. So once again, a lot of thought and care goes into the construction of these energy functions, which I could spend an entire talk on, but I only give you a rough intuition. That what we decided to do here was basically assign each pixel to a bunch of regions which are not specified. So this is where latent variables are starting to come in. So there's a set of regions that the algorithm needs to figure out. Each pixel needs to assign to a region, and then for each, so this variable RP gives us a pixel to region correspondence. And then for each region, we have some semantic category, what object class it belongs to, and geometry, is it horizontal, vertical, or sky. And we also have a single latent variable per image which specifies the horizontal line where we infer the horizon to be. That too is something the algorithm infers. And so those are the variables in the model. And so basically what the model tries to do is to assign each pixel to a region while preserving global scene coherence. And so this is the form of the energy function that we ended up constructing. And again, I'm giving only a very high-level view of this. We have a term that tells us what a reasonable position is for the horizon. It includes some kind of spatial prior over where the horizon is likely to be, as well as things like where vanishing lines end up. We have a region term that basically says that for a region of particular appearance, say green and fuzzy, it's more likely to be a tree, it's more likely to be vertical. You have other region terms for other types of regions like buildings and road and grass and car and so on and so forth. We also have a boundary term that tries to discourage having too many boundaries within a region while having strong boundaries between regions. And so that's this term over here. It encourages consolidation of the regions into larger groupings. And then my favorite term is this contextual term that, again, understands that tries to obtain some information from the scene as a whole. So, for example, it learns that regions that are labeled as car are more likely to be found on regions that are labeled as road than on regions that are labeled as water. And that's actually quite important because sometimes you can... I
called your microphone's turned too low.
I seem to be having problems with my microphone today. Okay, is this better?
Yeah.
Thank you. And this is quite important because roads and water are actually very similar in terms of appearance, and if you were just to use appearance of the single region alone, you would make very many mistakes, and this way it allows you to avoid many of these mistakes by using contextual information. And so that's the other term. Is this fine? Can I? Okay. Okay. So again, I'm not going to talk about the training until the later part of the talk. There's a lot of details there that one could spend a lot of time on, but here are some examples of the pixel level segmentation that this model gives. What you see on the left here is a segmentation in terms of semantic categories. Here we didn't try and distinguish between specific foreground objects, so all the foreground objects are labeled as with orange as foreground. We have another set of results where we actually did distinguish that way, but I want to get to the next part of the talk, so I'm not going to go there. And over here you see the labeling in terms of horizontal, vertical, and the gray is sky. And you can see that it actually gives rise to fairly decent pixel level segmentation of the scene. What can you do with a pixel level segmentation of the scene with semantic categories? It turns out that you can do some fairly interesting and sort of cool videos. So imagine that you have a single monocular image of the scene, and that you have understood where the horizon is, which you can see over here, that's the inferred horizon, and you know what's vertical and what's horizontal and what's sky. Well, once you do that, you could actually kind of draw a ground plane by assuming that the camera is about 1.8 meters above the ground, and place objects on the ground plane going into the horizon. And for an object whose bottom you can see, like the red object, you kind of know where to place it on the ground plane. The green object, its bottom is occluded, so you can't actually know exactly where it is. But you know that it can't be any closer than the red object, and you know that it can't be so far away that the bottom would be visible behind the red object. And so that actually gives you a fairly low uncertainty over where this green object might be, so we just take the midpoint arbitrarily. And so what that gives you is a fairly elegant reconstruction of 3D scene geometry from a single monocular image. So notice that the black things that you see here are not shadows. This is the occluded region behind the people in the original image that you don't know what's behind them. The shadows are actually going this way. But you can see that it actually placed the people and the other objects fairly correctly relative to each other on the ground plane. Does this help us understand scenes better? And the answer is yes. So let's look at some example images in this context. So here are the two most likely person detections using a state-of-the-art object detector using traditional methods. You can see that indeed the most likely person is this one, but the second most likely person is actually that sign hanging over there. The two most likely cars are actually here, this one and that one, and that is a cow. These are the results from our method that uses the context. We've lost this false detection over here. It correctly found and delineated the car, and it lost the cow. So this, of course, it's always good to find cute examples, but quantitatively one can also show that this gives significant improvements in performance. So if this is the baseline performance of your traditional object detector, what you see in the blue line is the improvement if you use this kind of region-based inference, and what this big improvement in performance is obtained by considering regions and context. You might wonder what that impressive red line is. That red line is a fictitious line. It's not a real algorithm. It's what you would get if you actually segmented the image correctly into regions. Then you could get a huge boost in performance. Now, of course, we're nowhere close to that, but it's nice to know that this is a viable trajectory for getting even further improvements in performance if we had a better segmentation method. Okay. So now let's talk a little bit about how we trained this and what are some of the issues, and this is where latent variables are going to come in again. So what is the fully supervised data that one can use to train a multi-class segmentation algorithm such as this? So you would think that we have available to us a fully segmented database where each pixel is labeled with the correct class. That would actually be incorrect. Such data sets are not to be found, certainly not in high numbers. So the Pascal dataset, which is one of the most commonly used, it's a competition that's run every year, and it makes a great effort to label images for both training and testing of computer vision algorithms. What it does is it labels foreground regions. So it segments out the regions in the foreground and annotates them with a class, but the background is just labeled with a generic background. So you don't know where the grass or the sky or the mountains are, and we saw that contextual features can be really important, but those are not labeled. Those are unobserved in the training set. In our data set that we use for training background, now has come to be called the Stanford background data set, we have, for most of the images, only labels of the background classes into 8 different classes, but foreground is labeled as generic foreground. And so we, again, don't have in a single data set full labels for both the foreground and the background. Now, even more to the point is the fact that there is a whole lot more images than in either of these data sets that are labeled at an even lower level of supervision, where somebody just draws a bounding box around an object and says, that is a bus, or that is a building. And that bounding box level annotation is, of course, considerably easier for a person to do than to segment out the specific boundary. You just basically draw the two points at the two edges of the bounding box. And so you can get thousands of images that are labeled at the bounding box level as opposed to hundreds that are labeled at the level of complete segmentation. But how do we use this as training data for a segmentation algorithm? And then, of course, if you go to ImageNet or Caltech or Flickr or any of or Google Images or any one of the huge image repositories out there, what you have is thousands or tens of thousands of images that are labeled at an even lower level, where you don't even get a bounding box, where you just said, this image is labeled with car, and you hope that whoever labeled it with car knew what they were talking about. And so the question is, how do you train with weakly supervised data? So we spent a bunch of time thinking about this, and how to train from a very diverse data set with different levels of annotation. And so what we ended up was formulating this as a set of constraints, the weak annotations, as a set of constraints on the true latent annotations of the underlying image. So for example, if this is my input X and this is my weakly labeled output Y, we'll notice that the hatched background indicates that it was only labeled as a generic background. What we ended up is basically in constraining the imputation of the latent variables, the inferred value of the latent variables, to be any value of the background classes. That is one of the 8 background classes that we permit, for example. So this is a constraint on the imputation of the latent variables. You can do the same with a little bit more thought. You can do the same with bounding box annotation. So for example, again, this is my X, this is my Y, and my latent variables specify exactly where the boundaries of the objects are within the bounding box, so the exact segmentation. And here, again, it's a constraint on the imputation of the hidden variables. This asserts that every row and every column in the bounding box must contain at least one pixel that's labeled with whatever class the bounding box was labeled as. So if this was labeled as cow, then every row and every column in the bounding box has to have at least one cow pixel. So you can think of it as a constraint, and you can put it into a constrained optimization algorithm. And I'm not going to talk about the technical details, but that's basically how it works. And then, moving on to even more weakly labeled images, if we just have that this, Y says this image contains a cow, again, the latent variables tells us exactly where the cow is and where the boundaries are, and the imputation algorithm that we're going to use says that the image must contain at least one region that's labeled as cow. Great. So now we have a solution. We can take weakly labeled images and put them into a latent variable learning algorithm. It's all going to work great. Right? Wrong. So just like the thing that I showed you before, latent variables are tricky, nasty beasts. So on the Stanford background data set, without all these thousands of weakly labeled images, we had a performance of 53.1. With it, the performance went up to a staggering 53.8%. Some classes got better, other classes got worse, but really the improvement in performance was negligible. And on the Pascal data set, it was basically a wash. So there we are. We put in all these additional instances, all this additional data, and nothing worked. So that was kind of a disappointment. The reason why this was disappointing is because imputing latent variables is hard. And this is sort of the running theme in both of these parts of the talk. You impute wrong, it introduces enough noise into your training algorithm that basically performance degrades more than you gain from having the additional instances. So that brings me into the second part of the talk. This is the more statistics part of the talk, which talks about learning with latent variables. And this is a joint project of my postdoc, Pawan Kumar, and my PhD student, Dan Packer. And this talk, if I have time, will have 3 parts where I talk about different ways in which one can improve learning with latent variables. So let me start with introducing the foundations in machine learning for all of the work that I'm about to present. And some of you might be familiar with, so I apologize for that. Please bear with me for a few slides before we get to the new stuff. So in 2001, Kramer and Singer came up with, I'm hoping all of you have seen a support vector machine. Okay, who's seen a support vector machine? Okay, awesome. So this is a multi-class SVM. Instead of just having a binary variable y that indicates the class labels, they have a multi-valued variable y that indicates one of several classes. And with that, they use the same, what you might call a log linear model, which has again, the weights that multiply with the feature vector, and then that is trained using an objective, using an optimization procedure that is effectively the same as what you get for the binary SVM. You're trying to minimize the norm of the weight vector W, as well as a constant C times the slack, psi I. So I'm also introducing some notation here, where the psi I is the distance between the objective function value, W transpose psi, for the ground truth assignment for the instance xi, which is yi, minus the value of the objective function for all other y. So you want the ground truth to be labeled to have a better value of the objective than all other possible assignments. And the slacks is what you use when you can't actually get that separability and you want to sort of allow the algorithm to pay for performance in some instances by reduced performance in other instances, or in terms of the norm W. Okay, so this is known as maximum margin training because it maximizes the margin, the distance in this space, between the ground truth label yi and all other labels. Okay, so that's in 2001. In 2003-04, work from my group as well as work from Thorsten Joachim's group expanded this to what's known as structured prediction. So structured prediction, instead of having just a multi-class y that has 10, 15 different values, now the y is what's called a structured output. So the y might be, for example, the assignment of values to every single pixel in the image. So if you have 10, if you have an image that's 1,000 by 1,000, that's 1,000,000 pixels. If you have 20 possible class labels, that's 20 to the power of 1,000,000 possible y's. So it's a very large structured output space. But it's not just a huge, unfortunately, 20 to the 1,000,000 dimensional vector. It has a structured form, both in terms of the construction of this feature vector. And so in this work, once you basically formulate the problem in this way, the optimization problem looks almost exactly the same as the multi-class SVM. You have the true target label yi, which in this case is potentially a full segmentation of the image. And for all of the other exponentially many possible assignments of the y, you need this to be better than this by some slack. The only difference between this and the multi-class SVM formulation is that we now introduce this loss function, which allows you to penalize some wrong assignments more than others. So for example, if your true ground truth is a certain segmentation, a y that only differs from it in 3 or 4 pixels, you might not want to pay for that quite as much as if the entire segmentation is wrong. So you can define an optimization loss that basically says how much do I care about one mistake versus a different mistake. So this is called the loss-dependent margin. Now, of course, this gives rise to exponentially many constraints because we have such a constraint for all of the exponentially many y's. Fortunately, in these two papers, it turns out that because the model is structured, you could actually optimize these tractably in a large range of interesting cases. So in the work that my student Ben Tasker did, it turned out that, and Carlos Gestrin, who is here. Carlos, are you here? Hi, Carlos. So tractable models that fall into a certain category, what's known as low tree width models, actually allow a polynomial size formulation. In the work by Suchandaritis et al. From Thorsten Joachim's group, they devised what's called a cutting plane approach, which is an iterative optimization scheme, which basically adds constraints one at a time as the algorithm continues to learn. And they showed that for many classes of models, after a polynomial number of cutting planes have been acquired, you're close to optimal solution. And so again, you don't need to ever look at the hugely exponential number of possible y's that define the constraints in this optimization problem. Okay. The next step forward came in 2008, 2009, the first by a paper by Feldenswalb et al., and then again work by Ewan Joachims from, of course, the Joachims group. And what they said is we can introduce latent variables into this structured SVM problem. So here we have not only, we now have a set of variables, input features X, we have a set of target variables Y, but we're also going to have additional latent variables, which we're going to denote as H. And now it's exactly the same philosophy as what we had before. We have the same kind of optimization objective. The only difference is that we now have to impute the latent variables H as part of our inference algorithm, because we don't have the true ground truth H. And so what we see here is that there's now an additional piece of the objective, of the optimization rather, this max over HI, which basically says what is the algorithm's best guess at the value of the latent variables. With that best guess, I want to be the best completion of HI of the YI, of the ground truth YI, should be better than some margin, with some margin than all possible completions of all other possible labels. So that's basically what this says. The best imputation of H consistent with my ground truth YI is better than any other imputation in any other label. So they came up not only with an optimization objective, but also with an algorithm called CCCP. I guess they weren't aware of the history of that, or maybe they were. But anyway, CCCP stands for convex concave programming, and what it does is effectively an expectation maximization like coordinate ascent. So you start with some initial estimate W0 of the parameters. You use that to impute the latent variables in every single one of my training instances using map inference, which is finding the best assignment possible. And then you update W by solving a convex problem, which is exactly the same that I would have solved had I had all my latent variables observed. Having done that, I go back and re-impute the latent variables, retrain W, and so on and so forth. And just like expectation maximization, this has the dubious guarantee of converging to a local optimum of the subjective function. So that's what you get. And the critical question is, how well can you impute HI? And for any of you who have actually played around with expectation maximization, or this algorithm for that matter, you know that this is a critical question. That is, the imputation of the latent variables, if you do it badly, just gets you into a very, very poor local optimum. So let's think about intuitively which imputations might be easy and which might not. So here, for example, is one image. We're trying to impute the background. And here, the sky is white, the grass is green, the road is gray. It's a trivial imputation problem, and the algorithm gets it right. Okay? Here's another one. The sky is white, the grass is green, the water is blue, the cow is brown, all is good. Another easy example. But not all examples are that easy. So here is an example of a cow. It might look easy to you, but if the algorithm hasn't really seen cows before, is it a cow? Is it a horse? Is it a cat? Is it a rabbit? I mean, who knows? And when the algorithm tries to impute it, it gets some weird mishmash of different classes where I think this is a sheep, and that's a mountain, or maybe a bike. I don't know. It's hard to tell from the green. But anyway, not so good. This one, the sky is red, the mountain's black, and you basically get complete gobbledygook in terms of the imputation. So here we turn to inspiration, for inspiration to human learning. And here's a cartoon example. Imagine that you're trying to teach somebody math and you give them all this information all at once. Like, bad local minimum. On the other hand, if you're a little bit more pedagogical in your view, you start out with one concept, moving on, and ultimately, okay? So let's try and be inspired by that in the context of getting our algorithms to learn better. So the idea here was actually proposed by Yoshua Bengio a few months before our paper came out. It's called curriculum learning. Start with easy examples and then consider hard ones as the algorithm continues to improve. The problem is, what's easy and what's hard? I mean, we've already seen that humans aren't necessarily that great at seeing what's easy and what's hard for an algorithm. And so how do we, and to be honest, actually asking a person to label what's easy and what's hard is a harder task for them than telling them to label whether there's a cow in the image or not. So we came up with an algorithm where the algorithm teaches itself, or figures out for itself what's easy and what's hard. So the idea is that the computer should figure out for itself which instances are hard for it right now, given its current state of knowledge. So this led us to an algorithm called self-paced learning, where we start with an initial estimate. I apologize, these A's should be Y's. I copy and paste on that local minimum. So we start with, so if we look at the original problem that we had, and now we basically are going to allow the algorithm to unilaterally declare that it's not going to look at some examples. So we're going to allow it to introduce a set of variables, VIs, where VIs are in 0, 1. VI says, if VI is 0, the algorithm at this iteration chooses to ignore this example. And what does that mean when VI is 0? It means that the slack doesn't count against it. So it can afford to mislabel it completely without any penalty. And that's effectively the same as ignoring that example. Whereas some examples still count with a value of 1, and those have to be used in training. So VI is equal to 1 for easy examples. VI is equal to 0 for hard examples. But in order, of course, you want to eventually incentivize the algorithm to use all examples. So, you want to incentivize the algorithm to use some examples, otherwise you can just choose to make all of them 0. So we add an additional penalty term that says that you pay for each VI that you make 0. Okay, so that there's a certain payment for that. Okay? Now we relax this integer program by turning this into VI in the interval 0, 1, and then it turns out that you can solve this using an algorithm called biconvex optimization, and basically alternately search over the space of VIs and the space of model parameters. So what does that imply? It means we start with an initial estimate W0, we impute the hidden variables, and then we update the weights by solving this biconvex problem, and then after having done that, we decrease the k, that is, we increase the penalty on ignoring examples, so the algorithm is forced at the next iteration to add a few more examples into the mix. So initially, the algorithm is going to choose to use only examples that it can label with fairly high confidence, those that are far from the decision boundary. And then as we anneal k, it has to get closer and closer to the decision boundary until ultimately has to use most or all of the examples. That's it. Design choice. So let me show you an example that's simpler than full multi-class segmentation because it's visually easier to understand. So this is the problem of object detection in an image. So this is a much simpler problem. You're given an image, and you need to figure out whether this image is an image of a bison, a deer, an elephant, a giraffe, a llama, or a lion. So here the X is the image, the Y is the label, and the latent variable is the bounding box around where the object ought to be. Okay, so you don't know where that is, even in the training data. And now you can apply standard, if you knew where H was, if you knew where the bounding box was, you could use standard computer vision techniques and do a good job, but the problem is that H is latent. So let's apply the two algorithms that we talked about, the original CCCP algorithm and our self-paced learning. And what you see here is the bounding boxes that are imputed by the two algorithms. And the blue ones are the ones that are used by the algorithm, and the red ones are the ones that the algorithm chose not to use at this particular iteration. CCCP doesn't get a choice. It has to use all examples, so all of its bounding boxes are going to be blue, but self-paced learning gets to pick which examples to use and which not, so some of the bounding boxes are red. And what you can see is that in iteration 1, the good bounding boxes are used by the algorithm. It knows that they're easy, and it chose to use them, and the bad ones are not. Okay? In iteration 5, it actually nailed this one, but it's still not sure enough, so it still decided not to use it. But by iteration 9, it nailed both of these, and it chose to use them. And by iteration 13, when it nailed this one, it chose to use that one as well. So it basically uses imputations when they're sufficiently good for them to be signal rather than noise. So this is, again, qualitative, quantitative results that show that this works. So this is test error for CCCP and for self-paced learning. This is for the deer class, and basically, actually, I think this is averaged over all of them. And it gets a significant reduction in error. We also have results like this for 3 or 4 other domains. 4. But I'm only going to show you results for this one other one. This is a result from a biological data set where what you get is whether a protein binds to a particular region of the DNA, but you don't know exactly where it binds. And so here you need to find what are called DNA motifs. These are little chunks of DNA that are characterized by these letters that tell us whether that is a good binding site for this protein or not. So here the X is the sequence, Y is bind versus no bind, H is the specific location where the binding took place, which we don't generally know in these kinds of biological data sets. And here also a big improvement in test error. Let me skip past this. This also works for more, for Pascal VOC, for example, which is for those of you who are in computer vision, care about this. Now let's go back to the image segmentation. Remember, we started out with the image segmentation. I showed you we added all this weakly supervised data, and it just didn't work. Now we're going to add all this weakly supervised data, and we're going to see if it works now. So here is the input. This is the state-of-the-art method that was prior to our work, and what you see here is that CCCP gave 53.8% accuracy, SPL gives 55.3. The improvement on, this is on the Stanford background data set, the improvement on the Pascal data set that has a lot more classes is considerably more significant. You go from 24.7 to 28.8. And you see that there's an improvement for virtually every one of the classes, and for those that it does worse, it only does very slightly worse. So now, finally, by being very careful in how we impute the hidden variables, you can make good use of data at different levels of annotation. That was the first piece. The second piece is, how much time? I think I'm good. Yeah, okay. The second piece is what we call self-paced model selection. So this was self-paced instance selection. Now I'm going to do self-paced model selection. All of you who've ever used support vector machines have been faced with the question of which kernel should we use. Should we use a linear kernel, which gives us a linear decision boundary, or a cubic or quadratic kernel, or which order of kernel should we use? And obviously, this is a standard Biasvariance tradeoff. You do this, you can't fit as complicated of a decision boundary, but you are less likely to overfit. Well, it turns out this problem is only exacerbated when you're doing latent variable learning. Because if you use an expressive kernel that can fit well the decision boundary, it really overfits in early iterations to impute it to latent variables that were wrongly imputed. And it can basically take the garbage imputations that you give it, it fits them really, really well, and then it has no incentive to change them, ever. And we'll show that in the results. On the other hand, if you use a simple low variance kernel, like a linear kernel, then it will never achieve a high level of performance even when the algorithm finally converges to good imputations because it has too high a bias, and it will never be able to fit the correct decision boundary. And so, again, we're going to use, give rise to human learning. So if you start out with the most complicated model, like, but if you start out with a simple theory, and then a slightly more complicated theory, and then an even more complicated theory, maybe it works. So, going back to the formulation as a latent SVM, this is my optimization problem. You've seen it many times. It hasn't changed. What we're going to do now is instead of using a single kernel, we're going to use a weighted average of kernels. So here we have a sum of different kernels, each of which is a kernel with a different complexity. And that effectively mathematically gives rise to an optimization that looks like this. And if you're not familiar with the math of support vector machines, feel free to ignore this. And what we're going to do is we're going to adapt the kernel at every iteration. So instead of having a fixed set of weights that have an average, that just pick a single kernel or a single weighted average of the kernel, we're going to let the algorithm select these coefficients A at every iteration so that the complexity of the model that is used by the learner changes over time, over iteration. So So this is an algorithm that we call by the font name SPAMKILL for self-paced multiple kernel learning. It starts with an initial estimate of both the weights and the coefficient A. It imputes the latent variable using the current weights and kernels. And then it updates both the W's and the A's by solving this convex problem. And this is done by block coordinate descent on W and A. Now, I think because of lack of time, I'm going to skip past the actual optimization algorithm and simply point out that when we're doing this, when we fix W and try and optimize A, it turns out that this minimization favors simple kernels, because it turns out that simple kernels have a lower norm in terms of the weights than complicated kernels. And so naturally, just by the way the norm works out, the algorithm is going to favor, by all else being equal, if you look just at the norm term, it's going to favor using simple kernels with higher weights, higher coefficients, A's, than more complicated kernels. And so what that means is the following in terms of the behavior, and I'll show you that in a moment. In early iterations, the HIs are incorrectly imputed. They're incorrectly imputed no matter which kernel you use. So for any given kernel, you're not going to be able to correctly impute the latent variables. That means that my slacks are going to be uniformly large. They're going to be large for the simple kernels. They're going to be large for the complex kernels. Because you just can't get the decision boundary right with the miserable... if you don't know where the bounding box is, you're not going to be able to get the correct classification. And so if the slacks are large, then the simple kernels are going to be preferred in order to minimize the norm. As the algorithm starts to converge, in later iterations, we have that the HIs are more correctly imputed. That means that they're more correctly imputed with the complicated kernels than they are with the high bias simple kernel. And so that means that my slacks are going to be small for complex kernels and large for simple kernels, which means that complex kernels are going to be preferred so as to minimize the penalty term on the slacks. Okay? So that's the intuitive behavior, and we're going to see that in the experimental results in a minute. So let me first convince you that this works. So this is the same image classification pass with the mammals that I showed you before. This is the training accuracy. This is the test accuracy. And what you see here are linear, cubic, quintic kernels and the uniform mix of the three different kernels. And what you see here is SPAMKILL on the right. And you can see that it gets better training as well as test accuracy than any of the other combinations. And if you add to that the self-paced learning from before, so you're doing both model selection and instance selection, the performance differential gets larger. So the combination of the two is better than just the one. Let me convince you that it actually does something sensible. So this is the cubic iteration. This is the imputed bounding boxes with the cubic kernel, the imputed bounding boxes of the SPAMKILL kernel, of the SPAMKILL method. And you can see that initially, at the first iteration, many of the bounding boxes are slightly or even totally off, as in the case of this giraffe over here. So this is iteration 1. Iteration 2, notice that the SPAMKILL bounding boxes got significantly better. These effectively stayed exactly the same. They moved around a little bit, but because it fit so well, there was no incentive to move them. It got stuck in this local optimum. And you can continue to see that these barely move, whereas the SPAMKILL bounding boxes continue to improve. And by iteration 5, these are mostly correct. And at convergence, the cubic kernel effectively is frozen almost exactly where it started out. Okay, and you could, again, quantify this. So what we see here is the intersection between the ground truth bounding box, which wasn't given to the algorithm, and the imputed bounding box. So did the algorithm recover the correct bounding box without being told what it was? And you can see that the cubic kernel very quickly asymptoted, whereas this continues to climb and asymptotes later and higher the SPAMKILL kernel, the SPAMKILL imputation. And you can see this when you add the self-paced learning component, the difference is dramatically larger. So again, you have the benefit of both algorithms coming together. Now, I told you that there is a natural self-selection process. That is, even though we don't tell the algorithm to prefer simple kernels initially, I told you that it would do that. And this is effectively the proof of that. So, not a proof, a demonstration of that, rather. So this is, again, x-axis is iterations. The y-axis is the weighted L1 norm of the Rademacher complexity of the case, of all the kernels. So that's a bit of a mouthful, so let me interpret that. There's a notion of Rademacher complexity which basically quantifies how expressive a kernel is. Okay? And what we see here is the weighted sum of the Rademacher complexities that the algorithm chose to use. So how complicated as an ensemble is the combination of classifiers that were used. And you can see that over iterations, this gradually climbs up by itself. We didn't have to tell it to use simple kernels first, or simple combinations of kernels. Over time, it gradually chose to increase the complexity by itself. And this is, I'm showing you one such example on one data set, but basically this is consistent behavior across all of the examples that we've done. Okay? Going back to the motif example, which is the other example that I've used. So here, it's not quite so clean, the story. So the linear kernels do really relatively well. The more complex kernels overfit badly, so they get much lower test accuracy. And then, fortunately, SpamKill doesn't do worse, but it doesn't do better either. But if you add SpamKill plus SPL, then you start, again, getting a significant performance improvement over just SpamKill alone, or just SPL alone. So, again, the combination of the two algorithms is more powerful than either one in isolation. Okay, I think we probably are largely out of time. So I will have to skip the section on embracing uncertainty. And I am happy to take questions about that offline. So let me just go to the end of this section. I'm always more optimistic about what I can cover than I really have time. Okay. Some cool graphs in there, and feel free to ask me about that. So to conclude the two parts of the talk, the first one is that pixel-level scene understanding enforces a coherence on the scene interpretation and consistency of context. And as such, it avoids labels like this. A cow, right there. You can see the cow? You can see the cow. There's the neck. You see the shoulder? No, just kidding. But on the other hand, in order to label pixel-level holistic models with a very deep annotation, is just intractable to do for very large amounts of data. You can get pixel-level annotations for certain amounts, for certain numbers of images, but not for tens of thousands of images. On the other hand, you can get lots of weakly annotated data. The second aspect, though, is that even if you can get a human to annotate the image, the human annotations are not always ideal to the task that you're trying to solve, and sometimes letting the algorithm decide on the latent variables for itself is actually a better strategy. Which brings us to the second conclusion, which is that we need to make better use of the data that we have available to us. Weakly labeled data, diverse data with different levels of annotation, data that's entirely unsupervised. And so latent variables are critical. So finally, the third conclusion is that you shouldn't jump too quickly if you're dealing with latent variables. You shouldn't try to immediately solve the hardest instances or use the richest model. Kind of like the way a person gradually learns over time, and for those of you who have children, you know exactly what I'm talking about. Initially there's large parts of the world that they don't even try and assimilate. They kind of find pieces of it that they can deal with. And then as their understanding increases, they interpret more and more of the world. And that it turns out that this kind of gradual strategy is also something that's beneficial, not just for people, but also for algorithms. Which brings me to, I found this self-paced learning in an article on the KQED website. This is on the Khan Academy. I'm sure many of you are familiar with the Khan Academy, which is a way of teaching children online on the computer. So I decided to use this interpretation. So with that, let me conclude by thanking the people who actually did this work. The work on holistic scene models on the outside, on outdoor scenes, was led by Steve Gould and Paul Kumar. Indoor scene models by Wang and Wang, and the latent variable learning by Karan Kumar and Ben Thacker, and thank you all for your attention. And I'm happy to take questions. Alyosha.
So I really like the same self-paced ideas and ways to not start a computer with all the stuff all the time. But what I'm not sure I understand with your instance-based selection is it seems like the initialization is very crucial because in a way you can exponential number of possible initializations and finding the right one could be an NLP hard problem in itself.
Absolutely, and we're we only have a heuristic for that right now. What we're doing is we're training a model for a few iterations and all the data that gives you puts you in the right space, and then I think we even trying to figure out if we did it without latent variables. I think we tried both strategies. And then with that, you pick usually at least half the examples because you don't want to have too small of a data set to work with. Now, of course, if you have a huge data set, you might be able to get away with a smaller fraction. But in our data sets, we picked about half the examples based on this criterion, and then we annealed it exponentially over time. But I agree with you, this does not obviate the need for initialization. This is not the silver bullet for everything having to do with latent variables. But it does provide consistent improvements on the actual performance that you get for every single data set that we've tried this. And we've done 5, I think, by this point.
I'm a little concerned about the very basic need to choose a particular age, particularly for situations where we have multiple labelings that can be simultaneously correct. For example, if you could recognize who people are, that's Anne, that's Joe, but you also want to know, is that a person? In some sense, you want to integrate over all the symmetries in the labeling.
Thank you for asking that question. The embracing uncertainty component that I had to skip effectively does but goes toward what you're looking for, in that we're not imputing a single assignment to the latent variables. We actually maintain a distribution over the possible assignments to the latent variables. And what it turns out to be, very beneficial to performance to maintain this distribution and count not only for how good the single best imputation of the latent variable is, but rather also how peaky the distribution over the latent variable is. So we use something called Renyi entropy, which turns out to be equivalent to an entropy term over the latent variables and a log likelihood term over the target variables y. And it turns out that optimizing the Renyi entropy gives much better results than picking a single best imputation over the latent variables. So your intuition is exactly right, and that was the third part of this that I had to skip the last time, and I'm happy to talk to you about that later. So thank you for asking that. That's it?
No more setups.
One more.
The idea of learning first simple instances and then going to harder instances is like the idea that boosting used in boosting and ensemble model used for learning different instances. Am I right?
Not really, because boosting in its traditional sense doesn't have any latent variables, and it's optimizing a convex objective. It's optimizing it in a particular way to hopefully get to to avoid overfitting to some extent. But it's still optimizing a convex objective, and what we're specifically trying to deal with is the non-convexity of any objective that involves latent variables. And that's true for the expectation maximization objective as well as for the latent SVM objective, that it's intrinsically non-convex and you're sort of traversing a very multimodal space, and the imputations are really critical to driving you towards a worse or better peak in the space. And that's what we're trying to address, is getting better imputations so you're driven to the right part of the space.
I think it's a great idea to learn when we proceed from easy to difficult. I'm wondering if it would help such a scheme is used in during inference, for example. So right now, inference is done by minimize a energy function. Is it better if we could, for example, detect or recognize easier things and then use this as some kind of prior knowledge to infer other difficult things during the inference?
I guess I'm not exactly sure what that means. Maybe we could take that offline because I'm not sure exactly what you meant. And I think we had one more question, two more questions, and then three more questions. Okay, people are finally perking up. Tom.
So the self-paced learning, you have these V's which determine which and when examples to pay attention to. I'm wondering if you could use a similar idea if I had my labels, say, in a hierarchy. In the sense of that would then give me. So, for example, suppose I had labels like vehicles and tanks and cars and so forth.
Yeah, that's a good idea.
Some kinds of labels might be easier. We might not know in advance whether it's easier to see it that it's a vehicle or a tank. But some things may be easier in the beginning, and then more of them might be easier to fill in subsequently. Can we do the same thing?
I think you could. We haven't explored that. I think it's a great idea. As you said, it's not clear that recognizing a generic vehicle is actually easier than recognizing a car. So I think there is some, it wouldn't necessarily, I think, be the case that the algorithm would choose the most abstract level of the hierarchy first and then work its way down. You could imagine that it an intermediate level and then work its way both up and down. But I think the same kind of, I would have to think about how to formulate this, but my initial gut reaction is that some formulation along these lines that would have not just an instance label VI, but an instance, label VI, so VIL, and would basically, do you want to try and label this instance as belonging or not belonging to this particular class? I think would be a very interesting way to go, and I hadn't thought about that. That's a very good idea.
Actually, Antonia Ferralbo has a NIPS paper coming out that kind of does that.
Okay, I haven't seen that yet, so one more. I think you had your hand up first.
Like, how do you tune the parameters, or how do you know when you succeed, or when you stop tuning it, or when it's not good enough and you have to try something else?
Which parameter?
I don't know. There must be a K or.
So, we used very simple rules of thumb for K. We used K that, as I said, gave us an initial, so that initially we were trying to deal with half the data set. And then I forget what we chose for the annealing parameter length. I think it was something like 0.8 or 0.9. So you got gradual addition of the examples, but not too many at once. We didn't have to tune that too carefully. I mean, it seems to work pretty well with reasonable parameter choices that were consistent across the different domains. So,
there might be other parameters that are not part of the algorithm, but when you run it, if it doesn't work, what will you do?
Well, what do you do when any learning algorithm doesn't work? Our experience is that we haven't seen it perform worse than CCCP. So it might not perform better, but we haven't seen it perform worse.
Yes, but when you compare with CCCP, it's that you already have the ground truth, right? You have the testing data, you have the visual level accuracy to compare it. So why don't you use it for training anyway? So why would we need
No.
data?
No. When I said compare to CCCP, I meant compare on the original objective, which is the ground truth Y labels, not the latent variables H. The latent variables H we used only for evaluating the algorithm to demonstrate that it's actually doing something. So when we're comparing to CCCP, we're comparing on predicting the target values Y, which you would do for any machine learning algorithm using a cross-validation regime or anything like that. So that's fairly standard machine learning methodology.
All right, so let's thank Daphne again. And there's a reception